Welcome everyone to this presentation of force identification in bridge using measured dynamic response. Today the presenter will be Øyvind Wiig Petersen. Those of you participating in this video recording will not be shown in the video unless you ask a question at the end, which I encourage you to do. And then, Øyvind, the floor is yours.
Thank you. So, good morning, everyone. I'm Øyvind. I'm a PhD candidate at NTNU, and my topic of research is the force identification in bridges using the measured dynamic response. This is our work that is supervised by Professor Ole Øyseth here at NTNU, together with Elise Marie Lorenz from TU Delft in the Netherlands. So the outline of today's presentation is as follows. I will start with some basic background for the research we do, and then I will define the inverse force identification problem, since I think that this is a relatively new term to most engineers. And then we move on to the interesting part, the results from the full-scale bridges we monitor, the Bergsøysundbrua and the Hardangerbrua. And in the end we will make some conclusions and summarize, and I hope also you will have some questions to ask me in the end. So let's start with the background of the research. I think you all are quite familiar with the E39 project, and from my perspective I focus on the long-span bridges, and especially the dynamic behavior of these bridges. And it is quite obvious that if you want to build new bridge structures that are quite longer than the existing ones and has new design concepts such as combined floating and suspension structure, then the dynamics of these structures are highly critical to understand in order for these structures to operate safe. In addition, we might have some new challenges in combined and wind and wave environments that we have not seen before. And it is important that we understand these wind and wave loads sufficiently so that the structural reliability is obtained. So the question we ask ourselves in my research is, do we know the excitation forces on these structures? Well, to answer that, we can have a look at some of the current tools for determining the loads from the wind and the waves. Well, first of all, we typically do some on-site measurements of wind or waves using masts or buoys. This is done prior to construction for an extended period of 1 to 3 years. We might have some section models in the wind tunnel or terrain models in the wind tunnel to understand the wind flow around our structures and in the adjacent terrain of the bridge. We might also perform some experiments in ocean basins for marine structures. And we often combine this with some load models we are able to obtain from a physical understanding of the interaction with the environment. And today we have also come far with computational simulations. This is again based on a physical model, some physical underlying equations that describe the problem. And lastly, we might have some experience from the engineering community. We have empirical formulas and also hindcast data from the bridge site under consideration. So these are quite a a large amount of sources that all contribute to determining the loads on our structures. However, we still think that the real loads have some uncertainties. There are always some simplifications and assumptions that we do. For example, the homogeneity and stationarity of the wind fields. We never know the true load combinations in advance, and we also make some assumptions on transfer functions, admittance, and so on. Sometimes the load mechanisms are also uncertain, and the measurements we do on site are what we call incomplete. They are measured at a limited amount of points. For example, the wind measurements, we cannot know the whole wind field in every point of the space around the structure. And we also have some uncertainties from scale experiments. For example, in the wind tunnel, we have a small scale model that we have to rescale to reality in order to have the real forces. And this introduces some uncertainties. And lastly, we'll always have some randomness that we cannot predict in the environment around the bridge. And in addition to this, from our research experience in our group, we see that we cannot always predict the dynamic response of the bridges very well. And all these points, they point to fact that the loads are not always well known. And this brings us to the inverse force identification. So in our structural system, it might be analyzed as follows. We have some underlying environmental processes that governs the wind and wave loads, and these are applied to the structural system. And due to the structural properties, we get some output response that is dynamic. And from this output response, we can always evaluate the different limit states we are interested in. We can check if the structure has sufficient capacity to withstand the stresses it is exposed to, and so on. So analyzing this problem from the loads to the response is what we call a forward problem. And this is what every design engineer does. He starts with an assumed load model, and then he creates a model of the structure, and then he obtains the output response, so either the static or the dynamic response of the structure. And this is in numerical terms, this is a quite stable problem. You usually have a unique solution, and as long as your computational power is there, if you have sophisticated software and so on, you can always solve this problem in the forward sense. But what we do in our research approach is that we do the whole thing backwards, and this is called an inverse problem. So what we start with here is the output response, and then we combine this with a structural system through a numerical model, and then we try to recreate the wind or wave loads on the structure. So this is called a force identification, or in more theoretical terms, sometimes we also call it estimation of input forces. However, this is not as easy as the forward problem, since it's highly numerically unstable. So the solution to this problem will always be very sensitive to noise in the measurement data or errors you have in your model. So this makes the problem quite challenging to solve. So now for some basic equations that describe how we handle this input estimation. So we might describe our dynamic system with the simplest equation of motion. Of course, for the bridges we will look at later, it's slightly more complicated. The equation of motion has more terms that we have to take into consideration, but let's start with this simple model. From this simple model, we sample some acceleration measurements or displacement measurements, and how we sample this, where we place our sensors and so on, is described by what we call the output equation. It describes how we sample our measurement data. And to get this problem on a mathematical form that we can apply later, we now make a redefinition. So we make a so-called state vector x, where we and velocities. And in addition, we define the force vector, which is the unknown system forces. And without going through the mathematical details, we're able to redefine our dynamical systems on state space form. So this again has a process equation which describes the dynamic in time, and an output equation which describes the measurements we make. In addition, we have added some stochastic white noise terms that has some covariance, and these terms allow for an uncertainty modeling, so to speak. So it is these terms that regulate the errors in a model and also the measurement noise on our measurement data. So these terms help later help filtering out errors that we cannot account for. So the reason we use this state space model formulation is that it's very compact and versatile for many types of bridges. And it is in fact widely used to model very complex dynamic systems. Many types of systems can be reformulated on this state space form. And these errors and model imperfections are also able to be described in the state space model. So we call this a stochastic deterministic model, since it all has the deterministic loads in addition to the stochastic noise terms. So the estimation of the states and forces is done by means of first establishing a system model in terms of these system matrices A, B, G, and J. We combine this with the measurement data we have and the noise model we have assigned. And today I don't think we should go to the mathematical formulations of these underlying algorithms, but feeding this model and data into the inverse algorithms gives us a state estimate x as well as an input estimate p. And to do this, we apply a range of different algorithms that are available for this. We in our research group focus on what's known as the Kalman type algorithms, and later you will see this denoted as JIS or DKF, or smoothing techniques or smoothing estimates. I have also given a year of development here on this slide, and as you can see from a research perspective, many of these algorithms are quite new, developed within the last year or the last 5 or 8 years. So this means that these algorithms have not been tested before on these type of bridges that we'll see. So we are also active in the development and testing of these algorithms in real life structures. There are also some other available methods that mainly perform some deconvolution in the time domain or frequency domain. And there are also some approaches that try to fit the unknown forces to explain the measurement data. However, we think that these methods are not currently ready to be tested to the large bridges. They do not simply do not perform well enough. So it's the Kalman type algorithms that we are using. Now, there are some important practical aspects we have to take into consideration when we do this inverse estimation. And the first thing is that a system model on state space form must be available. And usually this is not a problem. We can establish a system model through finite element models, for example. Secondly, the force locations must be known. So you have to know where your forces are acting on your structure. Alternatively, you have to identify a model force which encompasses all forces on your structure in a model space. And lastly, you always need good quality measurement data. In this case, it's the acceleration data that is most important. There are also some theoretical limitations to these algorithms. These can be formulated on a very strict mathematical form, but I think we'll define them here in a more loose form. Firstly, it's the observability. So the sensors has to be influenced by the modes in the system. So if the sensor cannot detect a mode, if it's not influenced by mode, it cannot pertain any information from that mode. And this leads to a loss of information that corrupts your problem solution. Secondly, and I think this is the most important limitation of the methods today, it's that the number of unknown forces cannot exceed the number of acceleration outputs. So the more forces you have on your structure, the more acceleration data you need to identify these forces. And lastly, we have a stability criteria, and this states that we always need some displacement data or strain data in order to have stable estimates. And this is due to the fact that accelerations cannot detect a constant force or a force that is very low frequent. So we need some preferably displacement or strain data to have a stable estimation process. So our research objectives in the force identification can be summarized into 4 points. The first objective we have is to acquire the full-scale measurement data from the floating and suspension bridges in Norway. And this consists both of accelerations as well as data on the wind and wave environment. Another goal is to develop the numerical models of the bridges. And if you are able to, we also wish to calibrate these models or validate that they are accurate using a system identification procedure from the measurement data. And of course, after this is done, we shall perform the input estimation using the measurement data, where we test these Kalman filter techniques, which is the state-of-the-art in this field. And lastly, we assess the performance of these methods. So when we obtain the results, we have to ask ourselves, are the estimation robust? Do we get accurate estimates? And does this methodology provide some useful information that we can used to better understand the loads and the dynamic behavior of these structures. So that was most of the theoretical background. We then move on to the more interesting part, which is the research results from the full-scale bridges. And we will start with the Bergsøysundbrua bridge. So for those who do not know this bridge from before, the Bergsøysundbrua bridge is a floating bridge just outside Kristiansund, and it is quite a unique type of structure. It is a bridge that is end anchored, so it's only supported at the ends, where we see some pictures here from the supports. And this bridge has a floating span of 840 meters. And this makes the bridge very flexible and susceptible to dynamic excitation of from wave actions on the pontoons. So on this bridge we have installed a monitoring system that consists of accelerometers, wave radars, anemometers, GNSS, or which is equivalent to a GPS sensor. And all this data we acquire is GPS time synced, so we know our time samples are accurate. And all the sensors, they send data to a local logger box on each pontoon, which then wirelessly transfers the data to a main logger box, which uploads the data to the internet, and we can access the data from our offices directly. So in order to establish a system model for this bridge, we consider it a linear system that is primarily subjected to wave loads. And in the next few slides we have quite a few set of equations. We will not go through all of these in detail. I will just keep them here for the sake of completeness, but we'll try to give a general overview of how we model this bridge. So the objective is now to create a reduced order model on a state space form. So to do this, we might start with the equations of motion in the frequency domain. And here we see that we have some frequency dependent matrices, and this is due to the interaction with the fluid. At the locations of the pontoons we will have some added mass and potential damping effects that are frequency dependent. And this is a big challenge in the modeling of these bridges. If we convert the equations of motion to the time domain, we see that we have some terms that are given by a convolution due to this frequency dependency of the mass and damping. And this is the biggest challenge we have in creating a time invariant state space model of this bridge. So our solution tool for this is so-called transfer function approximation, which is on the form of Rogers approximation. It is a rational transfer function that we use as a modeling tool to estimate this added mass and potential damping effects. So without going to too much mathematical detail, we first perform a model ordered reduction by so-called generalized shapes obtained from a eigenvalue problem of the system. And this problem gives us some reduced order orthogonal properties. It's similar to the obtaining the Nashville frequencies and damping of quite ordinary structures without the the fluid interaction. And here we have assigned a structural damping of 0.5%. So what we end up with is a time domain representation where we have a reduced order linear system, and we have a term that describes the motion-induced forces of the added mass and damping, and then our forces, wave forces on the structure, is described by they are transformed into a generalized space, which is given by these generalized modes from the eigenvalue problem. And I think we will not go through the details in this slide, but rather what we end up with is a very compact model that has two parts. The first part is a reduced order model for the contributions from the structure, the buoyancy, and the mass at the infinity frequency. And secondly, we have a subsystem that describes the hydrodynamic mass and damping. And we also have some coupling terms that describe the interaction between these systems. So what we end up with is a very compact state space model that we are able to use in the force identification. And the size of this model is quite small. This is why we call it a reduced order model. And this is due to the fact that we want to save some computational time in this inverse estimation. So the modeling tools we use to model this bridge is a combined abacus and Hydro-D model, where from abacus we obtain the generalized shapes, and the fluid structure interaction is modeled in Hydro-D, where we have panel models of the pontoons. So for the hydrodynamic fit, in this case, we are fitting the mass effects and damping effects of the fluid by a non-linear least square fit. And we see that from the figure that the parametric fit or the parametric model are quite well able to recreate the mass and damping effects. So this means that our model is very numerically accurate, even though it's a reformulation and a reduced order formulation of our original problem. I have also added some vertical lines to these plots that indicate the natural frequencies from these generalized shapes. And we see that these frequencies occur in the frequency range where we have a large variation of our parameters. So this testifies to why a high fidelity, very accurate model is important in this case. I don't think we can neglect the frequency dependency since these natural frequency lines occur along the whole spectrum of our curves. Okay, so that was a very quick view into the modeling of the structure. So now we get to the more practical part of the force identification. So in the marine structures, we may define the transfer from the waves into the loads and then into the response as follows. So we have the wave elevation process, which through some transfer function exerts wave forces on the pontoons, and through the structure we get some structural response. And this can be analyzed in two ways, as we have seen before. We have the forward approach and the inverse approach. And since for the Bergsøysundbrua bridge we have both acceleration data available, so the structural response, as well as the wave data available, we are able to attack this problem from both the forward angle and the inverse angle. So in the two approaches, we have the forward solution, which is driven directly by wave elevation data. And here we have to impose some assumptions on the wave elevation process in order to describe it in a statistical frequency domain. We have to assume that it is a zero mean stochastic process that is stationary and also homogeneous. So these are some somewhat uncertain assumptions, but they are necessary to make in the mathematical formulations we use. And in addition, we assume that the wave elevation can be described by a two-dimensional wave spectrum, which is also dependent on the angle of the incoming waves. And on the other side, we have the inverse identification of problems, inverse identification of forces, which is driven by the acceleration data, and we use here the state space model we have established. So in this case, we have no parametric model behind the waves or the wave forces. So let's start with analyzing the wave data. We have done some wave field estimation. Here we see an example of this for 4 selected recordings. So in these figures you see in the subplots that are denoted A, the directional wave field. And let's plot on a map of the local topology around the bridge. So here we see that we are able to quite well estimate the direction of the incoming waves, in addition to the frequency content of the wave or the wave process. And these different recordings, they testify to a quite large variety of wave conditions that can occur at this bridge site, which is perhaps something we would not have known without having this wave data. In addition, we can see that in the B figures we have the direction of the wind, and we observe that usually the wind direction, it corresponds to the wave direction. So it signifies that the wave field, the local wave field at the site, is mostly driven by the local wind. So in order to have the wave forces from the wave elevation process, we integrate over all the directions, and together with some transfer functions of the pontoons, we are able to have a power spectral density, which is a frequency domain representation of these forces. And this can also be transformed into the generalized space we are working in. So for our selected wave recording data, we get some first order wave estimates, which we think are reasonable. The biggest problem we see is that we get some very low frequent estimation errors in the low frequent range, and this is due to, we think, a sensitivity to the errors that are created in the very low frequency range. So apart from this, we think that the first order wave force content in the range of 2 to 4 radians per second is quite accurate. So now if we go to the second approach, the inverse estimation. We do this from the acceleration data, and we also create some synthetic displacement data by numerical integration of the acceleration data to have a stable estimation process. And in this case, we have used a recursive smoothing algorithm for the force identification. So if we use the frequency domain as a common basis of comparison for the force estimates from the two approaches, we see that for some of the forces, we have a quite good agreement between the two estimates. But we also have observed some quite large errors for others. So this brings us to a conclusion that this inverse estimation still has some problems in the accuracy of the estimation. And for now, we are not able to draw a quite clear trend in how these errors occur, when they occur, under what conditions, and so on. So this is something that we are looking into. But we think that this force identification has some potential if but there are still some challenges that needs to be worked out in order to have a good accuracy. And there are plenty of uncertainties in the analysis that are difficult to quantify directly. But for the forward solutions, we have the estimation errors in the two-dimensional wave spectrum. We also have some unknown or uncertain transfer functions for the pontoons. We have also made some assumptions on the homogeneity and so on that might not be true in reality. And in addition, we only investigate the first-order wave forces. So there might be some second-order contributions that we cannot model with this methodology. For the inverse estimation, it's mainly the model errors that are give some errors to our identified forces. And as mentioned before, the force identification is very sensitive to these errors. So errors in a model will always be a problem. And secondly, the methodology or algorithms in the force identification make some assumptions on the errors. They have to be so-called white noise errors, and in reality this assumption is violated. So we also have some uncertainty from that source. And additionally, we have some excitation sources that we have not considered, such as wind and traffic. We think that these are quite low compared to in magnitude compared to the waves, but they are still there, and we cannot really separate them from the wave force content. So another application to the data we have from Bergsøysundbrua is the so-called full field response estimation. So the figure shows the location of the accelerometers, and these are limited to the locations of the pontoons. So the question now becomes, can we use this acceleration data to say something about the accelerations where the cars drive, or the stresses in the truss, or for example the forces at the support point? Well, this is available through the state estimate, which was the variable x. So when we have our state estimate of the bridge available, we can, in theory, estimate the strains, stresses, sectional forces, and so on in any point of the bridge. And this is something we have investigated also. We have performed a validation of this using 3 selected recordings with some different excitation levels. So what we do here is that we estimate the displacement at the midspan, where we have a GNSS sensor that measures the displacements directly, and we try to use our state estimates at this point, or displacement estimates, and compare this directly with the displacement data from the satellite. And we see that we have quite a good agreement, especially for the vertical and lateral direction. However, we need some large amplitude excitations to really validate this, because in the satellite data we have a quite significant noise floor. So the GPS data can not provide millimeter accuracy for dynamic applications. But for the cases we have looked at, we have displacements in the order of 5 to 10 centimeters, and then we can see that we have quite a good agreement, and we think that in this case the state estimate is accurate enough to be used to describe the whole dynamic behavior of the whole bridge in a global sense. So our conclusions from the Bergsøysundbrua bridge is that the time domain models can be formed, but they are very accurate to the accuracy is very difficult to validate, because a system identification on a floating type of bridge has proven to be very challenging. The full field response estimation is quite feasible for the wave-induced response. But however, the identification of the wave forces is still a very difficult task, although we have some promising potential in the current results. At this point, we have some very large errors in our model, and some of these errors we are aware of, and we have some sources that we are probably not aware of, and this corrupts the accuracy of the wave force estimates. So for the floating type of bridges, which is a very complex case study, we think that a highly robust state and input estimation, for now it remains very difficult. So now we move on to some results from another bridge, the Hardanger bridge, and this is a quite different type of bridge. It's a 2-lane suspension bridge with a main span of 1.3 kilometers, and with these large spans, the excitation from the wind is of course very critical. The bridge also has a very slender design, which makes it very flexible. So in this case, it's the dynamic excitations from wind that is deemed most important. At this bridge, we have a monitoring system similar to the one at the Bergsøysundbrua bridge. Here again, we measure the wind velocities and the accelerations. So the challenges for the Hardanger bridge lies in the modeling of the wind field and in the aerodynamic properties of the structure itself. As quite clear from the picture in the slide, the terrain around the bridge site is quite complex, and this has some implications on the local wind field. So previous studies we have done, it shows that we have some directional wind effects. So the wind is different the wind field has different properties depending on if it comes from the east or west direction. We also have some wind coming from skew angles, which it's another source of uncertainty. And also the anemometer data we have is limited, so we can only measure at a limited amount of points, and we do not know what the wind looks like in between those points. And in addition to this, we might have some inhomogeneity or non-stationarity of the wind field that is different, very difficult to describe in traditional approaches. And also the uncertainties of the wind tunnel experiments. It leads to the fact that the wind loads are uncertain on this bridge, and therefore also the response effects. So our research solution to this is, of course, to assume that the forces on this bridge are unknown and identify them using the measurement data we have. So again, for this bridge, we have to establish a system model. In this case, it's much more easy than for a floating type of bridge. We create a reduced order model using the still air modes of the bridge. And this means that we consider the self-excited forces as an external force on the bridge, in addition to the buffeting forces, the forces from the traffic, and also if we should have some vortex-induced vibrations, the forces due to this are also unknown and collected in the unknown force vector. However, even though we we say that we are assuming the forces comes from the wind, the traffic, and so on, it is important to remember that from the mathematical perspective, these unknown forces have no specific source or parametric model behind them. So the forces we identify are always driven directly from the measurement data. So an important question for this system is how many modes should we include in the system model? And there are two aspects of this. The theoretical aspect is the limitations in the algorithms, which are limitations that can be formulated in a mathematical form. And there's also the practical aspects. So the model that we have should be able to describe the observed behavior. So all the modes that occur in reality should be included in the model. So if you look at some response characteristics of this bridge, we see the typical multimode response behavior. So very many modes contribute to the response. However, this is a obstacle to the application we perform on this bridge, since there are many unknown model forces. We also need many acceleration data outputs in order to identify these. And this is due to a theoretical limitation in the algorithms. So in this case, the theoretical requirements restrict us to only having 14 modes in the model, which go up to about 0.5 Hertz or 3 radians per second. So there are many modes above this frequency range that are excited, but we are simply not able to describe their behavior for now. So for the full field response estimation, in this case we have used a data set of 6 hours from a storm that occurred some 2 years ago. And in this case, the mean wind velocities ranged between 15 and 30 meters per second, which is quite strong. So here again, we perform a validation of the full field response estimation. So what we do here is that we take some so-called reference sensors that we remove from our sensor network, and then we use the data from the remaining sensors to estimate the response at these reference sensors. So these reference sensors are sensors that we use for validation purposes. And in the terms of accelerations, we see that we are quite able to describe the accelerations in the bridge girder. However, in the tower, we are not able to do so. This is the tower is the bottommost plot of this time series. And if we look at the frequency domain representation of these signals, we see why this is. We have a cutoff limit at about 3 radians per second, and this is the highest mode that we are including in the system model. So the dynamics above this limit we cannot describe for now, since we have a limited amount of acceleration data available. If we again look at the same estimates, but for the displacements rather than the accelerations, we see that we also have some quite good accuracy here. I think for the displacements, it's the low frequent content that is dominant. So here these 14 modes in our system model are able to describe the dynamics. One should note that the quasi-static response behavior is not available at this point, since our solution is obtained from acceleration data only, and this cannot describe the static behavior of the bridge. So the errors are reasonably low for the displacements, and we think that this proves the potential of this full field response concept in the suspension bridges. We have also performed some studies where we compare this estimated response with the response predicted from the design specifications. And without going through all the equations in detail, we see that we have some discrepancy between the estimated response and the predicted response from the design specifications. And this is a conclusion that we have also seen in previous studies of this bridge. And we think that this shows that there is many valuable lessons to be learned from the measurement data. It tells a story that reality might be more complex than we first assumed. And again, some more algorithm notice. We see that the different methods we use to estimate the response, they do not always give the same numerical value. And this is due to their different algorithm structure. Again, I don't think we should focus on this here. So there are many opportunities from this full field response estimation. For example, you can use this to quantify the dynamic bending moments. Here we see some bending moment diagrams from the duration of this storm. So maybe this can help us tell a story about the dynamic behavior of the bridge that we were not aware of before this. We can also plot the global response behavior of the bridge, and so also get a better understanding of the global dynamic behavior of the bridge. So that was the state estimation or response estimation, and the pure input estimation is still on ongoing work. So we have not look directly at our obtained wind force estimates, but this is coming in the fall of 2018. So our conclusions from the Hardanger Bridge is that contrary to the floating type of bridges, the accuracy of the finite element models are very good for the Hardanger Bridge in terms of the model properties. When it comes to the identification of the forces, we see that the multimodal global multimodal behavior is the biggest challenge for system inversion. So a system with many modes will always be very difficult to apply the force identification algorithms to. And this leads to a limitation. We can only partly describe the global dynamic response in a limited frequency range. So in order to improve this, we would have to install more sensors at the bridge. But all in all, we think that methodology opens up for opportunities to better predict the response effects on the bridge. So, for example, local stresses, which you can use to analyze fatigue. You can get a better understanding of the wind-resistant performance of the structure, and also some of the response that is not well explained by the current models. So to summarize our main findings for now, we see that the feasibility of these inverse identification methods depend a lot on the individual case. So it might work for one bridge, but not for the other. And this is due to the fact that these bridges has different sensor networks. They have different sources of uncertainties. The types of forces on these bridges are different. And also the level of complexity in the dynamic system varies from one system to another. So I think for now it's mostly the suspension type of bridges that can benefit from this type of methodology in understanding their behavior. However, in the future, we will continue to develop the applications to long-span bridges. And even though the robust estimation is still very difficult, we hope to continue to develop this in the forthcoming time. So that concludes my part of the presentation. If there are any questions, I'd be happy to answer. Thank you.
Okay, it is now open for questions.
Can I ask a question?
Yes, please do.
Thank you. Thank you, Øyvind. It's very good research and the presentation.
Thank you.
And very interesting. And can you show slides 20? I'm a bit interested in the identification of the hydrodynamic coefficients.
Yeah.
You have given, yes, this one. It seems like, what are the different results? Okay, one is from hydrod E.
Yeah.
And one is from the fate you have done.
Yeah.
It seems that they are perfect match.
Yeah. Well, they are very good, I think. So the more terms you include in this fit, or the higher order of the fit you use, the more accurate the fit will be.
So the first is this on the first column, the third one. What is with some difference? Which one is that?
That's 5.5, so that's the, let's see, it's the rotation about the y-axis.
Okay.
So, yeah, I think in this slide it's more apparent the rotation about the 5-axis here you see here.
And what is more interesting is that it can identify the damping so well.
Yeah, you mean the fit for the damping?
Yeah.
Yeah, it works quite well, we think. So we have tried a similar type of model fit for different structures, the floating type of suspension bridges where the mass and damping are a bit more complex, but we are still able to get a good fit for those as well, I think.
Yeah, also for the x-axis, it's the, what is that? It's
are you referring to one of the subplots?
yeah, any of it. So it's
yeah, the
circular frequency.
Yeah.
But then it seems that very high, a big part of the results are very high frequencies, right? It's 14.
Yeah. So the frequency range up to 14 radians per second is just the range we have exported from these HydroD programs.
Yeah.
Yeah.
But the most interesting part, of course, is around before 2, I think. That for the floating bridge.
Yeah.
But I think it's very good result because we have carried out model test, and we cannot get such good result. We did actually it's similar, I think, but it's more like irregular waves and measure the forces and fit for added mass and damping. A lot of them cannot get such good comparison.
Okay. Well, there are a number of ways to do this fit. In this case, we are fitting the poles directly, so it's the
you are fitting the
poles, the D variable you see here in the slide.
Okay.
So I know, for example, at the Marine Department, they have had some research earlier that fits. It's a reformulation of the fit where you fit another set of coefficients, and in this case, it can be more difficult, I think, to get a good fit, mainly due to the convergence of the minimization in the nonlinear least square.
Okay. Yeah. So thank you. It's very interesting.
Thank you.
Yeah.
Okay, thank you, Shu, for asking questions. We're running a little bit out of time here, but if anyone has a quick question more, you might want to ask it now.
Hi, Øyvind.
Yes.
About the thanks for the presentation.
Thank you.
About on page number 10, you spoke about the number of data points for acceleration and let's see. Yeah.
Here.
Yeah, you spoke about the solution depends on the number of acceleration points.
Yeah.
Data points for acceleration.
Yeah.
And I'm assuming you calculate the velocity by integrating it. So did you mean the number of data points for acceleration over time, or do you mean number of sensors?
No, the number of sensors.
Right.
So this invertibility property is a very strict mathematical property that says that if you have a number of acceleration outputs, it can only it cannot describe an infinite amount of unknown forces. So in the mathematical terms, this would be a sort of rank deficiency if you are.
Yeah, so you can only get as many variables output as you have input because it won't be solvable. Yeah, but then can't you linearly interpolate between the accelerators that or sensors that you have to get a higher number of points?
You could. I think that would be a very crude solution. Then you make an assumption of a linear behavior between two of these, and this might introduce some errors in the output data. And then, as we have seen, the identification problem is highly sensitive to these errors. So I don't think that's a very good solution. Ideally, you need direct measurements.
Right. And how many points did you do the wave measurements at? I'm assuming 1.
It was 6 points. We have 6 wave radars.
Ah, right. Okay. Okay. Thanks.
Thank you.
Okay, thank you. And I would just like to remind everyone that we have also a new presentation next Friday, where Joar Tistel will present bridge foundation on large water depths. So I would encourage you all to be back here next Friday. And then, since I don't hear any more questions, I would thank you, Øyvind, for a great presentation, very interesting, and also good questions. And then I would say thank you.
Thank you. Thank you for listening.